In order to talk about binomial radical expressions, we're going to start by talking about how we add and subtract expressions that have radicals in them. We've already done some simple multiplying and dividing, so I'm going to start you off with something that you should know how to do. If I gave you the problem, the square root of x plus, let's try that again, simpler. If I give you x plus 3x, and I said add them, you'd be able to tell me it's 4x. Because they're like terms, and when you have like terms, you just add the coefficients, the numbers in front. Well, if I made this problem x squared plus 3x and said add those, you would tell me it's x squared plus 3x because x squared and x are not like terms. Well, now I'm going to change this to have radicals in it. I'm going to say the square root of x plus 3 the square root of x. The answer is 4 the square root of x. Radicals work like terms, but in order to be like terms, they have to have the same radicals. So they both have to be square roots, or they both have to be cube roots, or they both have to be fourth roots, and they have to have the same expression under the radical. So, for example, I could not combine these. I could not combine these. They have to have the same root index, and they have to have the same term or expression under the radical. So let's do a problem where we simplify. I'm going to start by reiterating what the phrase simplify means, because we have 3 words in math that we use a lot. They are simplify, evaluate, and solve. Simplify is something you do to algebraic expressions that have variables in it. When you're done simplifying, the answer still has variables in it. Evaluate is something you do when you plug a number into an expression, or if you use the order of operations in order to break down a problem into a single numerical answer. The bottom line is when you evaluate, the final answer is usually a number. Solve is something you do with equations, i.e. it has to be something that has an equal sign in it. So in these problems here, we're going to simplify. So 3 the square root of 5x minus 5 the square root of 5x is 1 the square root of 5x. You don't have to write the 1. We would normally write the answer just like this. Because they both had the same radical with the same expression underneath. In part B, 6x squared the square root of 7 plus 4x the square root of 5. They are not like terms because they don't have the same thing under the radical. So we say it's already simplified, or cannot break down any further. C, 12 the cube root of 7xy minus 8 the fifth root of 7xy. Watch out, because they do have the same thing under the radical, but notice this time the root indexes are not the same, so watch out for things like that. We cannot do anything more to this problem, so it is already simplified. In problem 2, I'm going to talk about this problem in 2 different ways because students have different understanding levels of number theory. I want to simplify the square root of 12 plus the square root of 75 minus the square root of 3. Upon first glance, you're like, oh, well, they don't have the same numbers under the radicals. However, you have to first ask yourself, can those radicals be simplified? Because they can. One of the ways that we simplified radicals was by rewriting the number under the radical as the product of 2 numbers where one of them is a perfect square. The reason we're looking for perfect squares is because we're taking square roots. If these were cubed roots, I'd be looking for perfect cubes. So 4 times 3 is 12, where 4 is the perfect square. 75 is 25 times 3, And you can't do anything to the square root of 3 because 3 is a prime number, so it can't be broken down anymore. Then the next thing you do is you take the square root of those numbers that are perfect squares. So I can rewrite this as 2 the square root of 3 because the square root of 4 is 2. Remember, when you take the radical of a number, the radical then goes away over that term. So it would not be correct to write that the square root of 4 is equal to the square root of 2. That is a common mistake that many students tend to do. What you do is you tell me this. However, the 3 that's underneath stays there because I couldn't take the square root of 3. In the next term, I would rewrite this as 5 the square root of 3, and then minus the square root of 3. So now they all have the same radical, and all I have to do is add their coefficients. 2 plus 5 minus 1 is 6. But I couldn't do that until I broke down and simplified the square root of 12 and the square root of 75. I'm going to do this one more time using the factor tree method because some students like that better. So I could break down 12 by doing 2 and 6 and 2 and 3. So I could rewrite that as 2 times 2 times 3. 75 is 3 times 25, which is 5 times 5. So I can rewrite that as 3 times 5 times 5. And then again, I can't do anything to 3 under the square root because it's already prime. Then I would look for pairs of the same number. I have one pair of 2's that I can take out, and I have one pair of 5's that I can take out. And I end up in the same place I was in the last part of the problem. So the answer is still 6 the square root of 3. Alright, in this last problem we're going to do a problem where we're going to find the perimeter of a stained glass window using our understanding now of radicals. So I want you to look at this stained glass window design, and there are all these squares inside of it. Well, in order to find the perimeter, we have to remember what perimeter means. And perimeter means add all the sides. So in order to add all the sides, I gotta find the length of these little pieces here, don't I? Well, if you look at those, these are the diagonals of those squares. And there are 10 of them. We'll worry about the corners in a minute. So I need to find the length of the diagonal of one of those squares. So if I box this, each of these squares has a side of 5. I want to find the diagonal. Well, remember that not only do squares have all the side lengths being the same, but all the angles are 90 degrees. So if I want to find the diagonal of a square, I'm going to use the Pythagorean theorem. The Pythagorean theorem was the one that said a squared plus b squared equals c squared, and c has to be the hypotenuse of the triangle. This is the hypotenuse. So I'm going to do 5 squared plus 5 squared equals x squared. So 25 plus 25 is 50. And then I have to take the square root of 50. But I need to simplify that radical. I'm going to do this the short way. If you would like to do it using the factor tree, you may. 50 is 25 times 2, and the square root of 25 is 5. So each of those little pieces, all those diagonals, are 5 the square root of 2. There are 10 of them, so there's 10 times 5 the square root of 2. But that's not all of my pieces. I have some little corners here that I got to deal with. Okay, the little corners, they're not a total square themselves, or they're not a total side of a square. But I can tell you that this side of the square is 5 inches long, because that hypotenuse of the little square, let's draw my little square here, is the side of one of the squares. I just don't know what these little corners are. So why don't we use the Pythagorean theorem again? So x squared plus x squared is equal to 5 squared. Now, here's the fun part. What's x squared plus x squared? It's not x to the 4th. That's what you get when you multiply them. It's actually 2x squared equals 25. This probably wasn't a good one to use for this, because now I'm going to get x squared is equal to 25 over 2. Oops. And then when I go square root it, I'm going to get x is equal to 5 over the square root of 2. Ew, I don't like that. I should have used a nicer number, but that's all right. All right, we don't like radicals in the denominator of fractions, and we've already learned how to get rid of this. And this becomes 5 the square root of 2 over the square root of 4, which is 2. Now the next thing is, how many of those little pieces are there? Well, let's go back up here. There was 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 of these 5 the square root of 2 over 2 pieces, plus 10 of these 5 the square root of 2 pieces. So let's see, I'm going to get 40 over 2, which is 20 the square root of 2, plus 50 the square root of 2, which tells me the perimeter is 70 the square root of 2. The problem that's in the book is a little bit different, because they give you one that doesn't have these little corner pieces that you have to deal with. I like doing more complicated problems in notes. So that is the beginning of binomial radical expressions.